All right. Well, hello everyone. My name is Marie Griffith, and I am an undergraduate senior from Grand Valley State University. And I'm also a McNair Scholar, so I would like to thank the McNair Scholars Program and the TRIO program for funding me for this research. And my project is modeling the development of world records in track and field. Now, for my overall research goal, it is believed that there is a human performance threshold limit for every track and field event. The goal is predicting these, and in these predictions, it is also believed that there will be asymptotic convergence that happens along these thresholds. So the world record data will form a curve that will run along the asymptote without touching the limit value. Now, this research has been done before, and in the literature sources that I review, the most common technique for doing this modeling were curve fitting techniques. So you test out a bunch of curves to see the quote-unquote best fit for the world record data. And in this project, it was done on the 100, 200, 400 meters, the long jump, and the shot put. Now for the models and curves that I've tested, one, the linear model, this did not work out too well because the linear model is saying that there is a constant decrease in the world record until it reaches zero or the asymptote, which is not the case. The second curve would be the exponential curve. Now, in the exponential curve, it was a little bit better fit than the linear model, but it's still not completely accurate because it's still saying that the world record will still steadily decrease until it reaches the asymptote in a curve-like form, which is not the case. Now, there was a debate on whether to use the logistics curve or the Gompertz curve because they both are appealing because of the potential S pattern shape that they can make. But ultimately, the Gompertz curve was chosen because unlike the logistic curve, the two tail ends of the graph do not have to be symmetric or identical. So in other words, for example, in the men's 100 meters, this tail end and this tail end do not have to be the same, and they do not have to be symmetric. So ultimately, the Gompertz curve fit the data the best. And from this Gompertz curve, the Gompertz model that was computed had the following components. Y of t would be the threshold year for year t. A would be the slowest time or the lowest measurement. B would be the fastest time or the highest measurement. C would be the growth rate or the change in time or measurements. D would be the inflection point, which changes the curve direction. And T would stand for time. And in this case, time would be the year from the first recorded world record until the year 2014. Now, from this model, I was able to predict threshold limits. Here in black are the current world records as of the year 2015, and in red are the computed threshold limits by the Gompertz model. So after this was computed, there was a procedure called sensitivity analysis, or playing around with data, that was conducted. So in this sensitivity analysis, the current world record for the 100 meter dash was extended for 100 years to see if the threshold limit would change. And indeed it did. If we were to extend the world record of 9.58 for 100 years, the threshold would change from 9.36 to 9.55. Same for the women. If the world record of 10.49 was extended for 100 years, it would change from 10.06 to 10.47. Also, in the sensitivity analysis, the current world record holders of the 100 meter dash were taken out of the analysis to see if it would affect the limit values, which indeed it did. So what this tells us is that for closing arguments, while in theory a definite limit value for track and field events exists, thresholds can change over time because there is a change in time period and a change in fluctuation in the human performance. So therefore, there is not one definite threshold limit for every track and field event. It constantly fluctuates. Once again, I would like to thank the GVSU McNair Scholars Program And I would like to thank my awesome mentor, Dr. Paul Stevenson, for conducting research with me. And I would like to thank you for listening. Thank you again.